Welcome back to week 4 discussion on bonding, in particularly electron geometry and valence shell electron pair repulsion theory. Okay. In the previous video, I introduced you to the concept and how the lone pair or electron pair on the central atom determines the molecule's polarity. Okay. Let's look at two more examples in this video and then two more in the next one. Okay, let's look at BeCl2. Okay, beryllium, okay, as a Roman numeral of 2A, and Cl, as always, has got 7A. Right? This means this has 2 valence electron, and this has 7 valence electron. Okay, that means, as I've always said, the element that's least in count goes at the center, and the element that is least in number goes on the outside. Okay, right. Now beryllium has only got 2 electrons, so I'm just going to position them in such a way it faces the chlorine. Now again, all this is pretty arbitrary. The chlorine could be here or it could be here. Okay, that is not the point. Okay, you just have to get them someplace, and then let's go get a different color for our chlorine. As I said, when your electron count is 3 or more, then you put them in pairs. So I got 7 electrons, so I split them in pairs of 2, and there's an odd electron. Similarly, there's an odd electron and pairs of electrons. Okay, now let's go get a pink color. Okay, now we just connect the blue and the black, blue and the black. All right, so now that's it. We have used all the electrons and there's nothing left, right? As I said earlier, the central atom, we're going to call it X, and however many outer atoms we have, we're going to call them X. So we got 2. There is no lone pair if you see on the central atom, so you don't need to write E, right? And this is linear. Okay, AX2. I will summarize all this in the very end, but for now, take my word for it. This is the electron geometry of AX2, which is linear. Okay, now let's try a different compound, which would be water. Okay, you would think because it's got 2 oxygens and a hydrogen in the middle, it will also be linear, but you would see. So before that, before we move to the next molecule, let's wrap this one up. Okay, so let's go get our red, right? And if you look at your electronegativity table, beryllium is got 1.5, chlorine is 3. Clearly, clearly beryllium is smaller, so in electronegativity, so it gets the tail and this gets the head. And similarly, this gets the head and this gets the tail, right? So the bonds themselves, what did I say? 1.5, 1.5. Beryllium is 1.5 and chlorine is 3.0, right? Beryllium is 1.5 and chlorine is 3.0. Clearly, it's 1.5, which is within the range of 0.6 to 1.7, right? Or 1.6, sorry. So that is polar covalent, right? The bonds themselves are polar covalent, but the molecule itself is nonpolar. Okay? That's because the molecule is nonpolar because this arrow is pulling this way, this arrow is pulling this way. So if I write it, this is what's happening, right? Again, they oppose each other and they cancel out. Okay, so that's why this is nonpolar. Now let's go to the second example that I want to go over with. Let's go get our black. Let's write water. You would think this is very similar to BeCl2, which we just did. You got 1 central atom, 2 outer atoms, so that's also should be turning out to be AX2 and linear. It's however not the case. So let's go get the Roman numeral. Oxygen, hydrogen is 1A, so it's got 1 valence electron per hydrogen, and then oxygen is 6A, so it's got 6 valence electron, right? And as always, you put the oxygen at the center because it's least in count, and you put the hydrogens on either side. Okay, now hydrogen's only got oxygen's got 6 valence electrons, right? Right. Let's go put them around 1, 2, 3, 4, 5, and 6, right? Now let's get a different color for our hydrogen. So it's only got one, so we don't need to, right? It's only got 1 electron. Now let's go get our pink color to be consistent. Okay, connect the blue and the black, blue and the black. Now there's still 4 electrons left on them, right? So here's how I'm going to write them, right? So we've already made the bond. I'm going to collect them into 2 pairs. Okay, there's 4 electrons left on the oxygen, so we are going to write them as 2 pairs. So the central atom is A, 2 outer atom is X, so X2. There's 2 lone pairs, and E is what is used to refer the lone pair, so it's E2, right? This is called bent. Okay, I will not give this attachment on the test. This is something you would have to remember, but it's not hard. There's a recurring pattern. Okay, there's a recurring pattern. Now let's go get our polar bonds. Oxygen, I believe on the electronegativity table is 3.5, hydrogen's 2.1, right? Oxygen's 3.5 and hydrogen is 2.1, right? So that means hydrogen is less electronegative, oxygen is more electronegative, so it points out this way, right? Now because of this lone pair, okay, right, if you think about it, it's like this, right? Because of this lone pair, it's pushed down. That means both arrows are facing towards each other, so it comes down to be like this, again in one direction. There's nothing to oppose it. Because of this electron pair repulsion between the 2 pairs, it's pushing the oxygen and the hydrogen. It's like the flap is going down. Okay, it's bent and the molecule is polar. I'm consistent with my statement. As I said, typically when you don't have E's, the molecule is nonpolar. Typically when you have E's, then it's polar. Okay, so this is technically what you may have to memorize, but this you don't need to memorize, so is this. Okay, the moment you see E, it's polar. The moment you don't see E, is nonpolar. And all this you don't need to memorize. You don't need to memorize the values. You just have to understand most of everything on the screen. The only thing you would have to memorize is this, which is not hard. I will give you a list of 6 in the very end. That's not very hard to memorize. Okay, which is why, remember I said a solvent, water is the universal solvent and it's polar. This is exactly the reason why water is polar. If it's not for that, I don't think most of us would be drinking water today or use it for so many purposes. Water is a universal solvent that's used for so many countless purposes, and if that was not to be the case, then guess what, we probably will not be surviving. All right, so that's that, and then let's go get our next compound. Okay, so let me go get my black. Next compound we're going to look at is methane. Okay, I will finish this video with this compound discussion, and in the next video I will wrap up the remainder too, and then we can summarize the complete list of AX and then whatever that is, whether it's bent, linear, whatnot. All right, so carbon is 4A and hydrogen is 1A. Okay, so that means it's got 4 valence electrons and hydrogen's got one valence electron per hydrogen, right? And being consistent with it, the carbon goes at the center. Just put the 4 hydrogens around it anywhere you like. Okay, now let's go put the 4 electrons facing the hydrogens. Again, all these are very arbitrary. If your hydrogen is slightly skewed than the one I'm drawing, it's no big deal. All right, so now let's go get the 1 electron that's available from each hydrogen, facing the carbon. Okay, all this is arbitrary, the position of the hydrogen, but you do want some separation. So let's go get our pink back. Okay, we connect the blue and the black, blue and the black, blue and the black, blue and the black. All right, now clearly we know, I think from our earlier discussion, that carbon is actually less electronegative. Carbon slightly more electronegative than hydrogen. So this is 2.5, this is 2.1. The difference is 0.4, right? So technically we don't assign any charges, right? En equals 2.5 minus 2.1, which is 0.4, and this is within 0 to 0.6. So this is non-polar covalent. Okay, so there is no discussion that this would ever, if the bonds themselves are non-polar covalent, that means the molecule has to be non-polar overall. Okay, so this is, if you write the structure, it will be A, we have 1 central atom, 4 outer atoms. There is no lone pair on the central atom, so it's AX4. It's called tetrahedral. As I said, this is the only thing you have to memorize, okay, right here. Everything else you can get from just doing the process. This is the only thing on the screen that you would have to memorize. I mean, the rest, if you want to even find a mnemonic for it, tetrahedral is 4, so there's 4 bonds, and that's why it's tetrahedral. Okay, so this is the only thing, I mean, on a long list of things, it's the only thing you have to memorize. Pretty much you can get everything from either the values, you can get them from the electronegativity table that I provide, and then drawing the structure, you just have to understand it, you don't need to memorize it. And then the AX4, you can just get it straight off the structure. So there's really only one thing that you have to remember or memorize, is the actual name, the geometry's name. It's tetrahedral. Because we don't even have polar covalent bonds, because we have non-polar covalent bonds, the overall molecule is non-polar. It is that simple. So again, you don't need to memorize this either. There's only one thing that you do have to memorize, which is this. All right, so that's the discussion. I do want to stop the video here. We got 2 more compounds to go, and I will come back and wrap this VSEPR discussion in the next video. All right, stay tuned.